Okay, okay. Let's see. I had made a prediction that there would be 15 people in class. 4, 8, 9, 10, 11, 12, 13, 14. Off by one. Pretty close. Okay. Including myself is 15. No, no, no. That is 15. Okay. So, okay, good. See, this is what a professor is supposed to be good at, estimation. Okay. So today's lecture is on learning manipulation. So this is the second last lecture. The next one will be on language models. And this lecture I want to be very interactive, okay? Because I think what we've covered the basics in the class. This is more about current work. All the papers I'll talk about are 2024 papers. So it's really meant to be an open discussion. Okay, so what I want to start with is what's the big picture right now in how people are thinking about developing policies for manipulation. There are two big approaches. There are supervised learning and there's reinforcement learning. And everything is a combination of the two in some form or the other. So what is the dominant paradigm if you look at the popular press and if you look at the companies, it's supervised learning. And somebody sent me a link to an article in the New Yorker, which was talking about the Google effort in robotics, and that was all in the supervised learning paradigm. I'm not quite convinced. I think actually multiple approaches are needed, and the current supervised learning paradigm is not the final answer. But this is a very debatable topic, and I hope we'll have the debate during this lecture. But first, I want to set the stage by talking about the dominant paradigm, which is the supervised learning paradigm. And essentially, in this paradigm, you collect a whole bunch of demonstrations by teleoperation, and then you train a diffusion policy on top. That's the very, very short summary of what's the leading paradigm. Let's get a bit into it, and I'll take you through this. So first of all, that there are a number of different hardware solutions that people have proposed for collecting teleoperation data for manipulation. And here is one. This is called Aloha, which became Mobile Aloha. Then there is something called Aloha 2. Maybe there is an Aloha 3. Yeah. Huh? Aloha Unleashed, that's the one from Google. Okay, so Aloha X, okay? So I have this paper is I think this is probably called Aloha 2, this one. No. This is a later one. This is not the first Aloha. This is a slightly later one, I think. But the one at RSS 2023. Okay. I mean, there are archive papers, there are conference versions, so I'm not going to get into the archaeology of this. So this is the setup. So the setup, as you can see, is bimanual. There is the configuration is that it's sometimes called puppeteering. So one person is manipulating these two arms, and then there's a gripper. So essentially, you have how many degrees of freedom system? 14, right? 6 degrees of freedom for the arm, and the 7th degree is the gripper. And 7 times 2 is 14. Okay. What's the hardware? It's a parallel jaw gripper. And the sensing is that there are multiple cameras. There's a camera which is the important camera is the one at the wrist. Okay. So the one at the wrist which looks very closely at the object when you are approaching it. So it's essentially doing some kind of closed loop with vision in the loop where the vision camera is at the wrist. Okay. And so this paper, which is from RSS 2023, which is like just a year and few months ago, but it already seems like ancient history. So what they showed were a series of teleoperated skills, and these are examples here. Threading a zip cable tie, slotting a battery, opening a lid, manipulating tape from a dispenser, things like that. Okay. And this gives you more of the hardware setup. So there is bimanual, there's a wrist camera, there's a top camera, and there's a front camera. Okay. And the arm which is being used is not a super high precision arm. So the accuracy here, they've listed the repeatability is on the order of a millimeter. So one of the advantages of this is that this is a relatively cheap setup. I mean, there are industrial robots which are much more accurate in terms of their repeatability is much smaller than a millimeter, but it comes at a cost. And the point here is this is a much cheaper setup. Okay, so is the hardware configuration clear? Now, this is not the only setup for collecting data with teleoperation. There are many setups which are around. I won't get into them in this lecture. From Shuren Song's group, there is something called UMI, Universal Manipulation Interface. There is one from here, Hato, that Toru was responsible for creating, and there are many others. So ones which start from sort of a AR, VR type devices, okay, and then build out from there. There are these kinds of configurations. I'm sure there'll be many more coming up. But the central aspect here is there's a human who is going to do the task, and then we'll collect trajectories, and then after collecting the trajectories, we'll train a policy. And essentially, there are two ways. So that's a supervised learning framing of the problem, right? You collect trajectories. So in computer vision, in the good old days, what did we do? We had lots of images, and then we said tiger, zebra, horse, etc. Or other versions of supervision was marking the boundaries of an object. So this is the same thing in a robotics context. Except I think that this job is a more painful job for an operator. I think the computer vision job of looking at an image and saying tiger or zebra is probably a more fun job, I think, anyway. This is more tedious. I think people who do this, they get tired after a little while. That's fine. Okay, so now you collect these trajectories. Now, how do you build a model? What you're trying to build is a model which says, given a certain observation, and the observation here would come from these wrist cameras plus proprioception, you're trying to predict the action, right? Action will be in a usual setting of joint angles or the delta of the joint angles. That's the, I won't go into those kinds of details here. Okay. How do you take the trajectories that you collect like this? And the typical number is in the thousands. So the Aloha Unleashed paper from Google, they have like 27,000 trajectories or something of that order. And the work from Physical Intelligence, which is the company with Sergey and Chelsea, they have a model which they call Pi0, and that's based on a large number of trajectories that they have collected. So you can imagine the game. Thousands go to 10,000s, which go to 100,000, which go to million, whatever. And yeah. How do I use the trajectories to train a model? This paper uses what's called an ACT, Action Condition Transformer. And at the same time, I think from the Shuren Song and the TRI group, there was a diffusion policy. So these were, I think, two competing approaches which came out about the same time. I think the diffusion policy has won out. So it seems the later works are just going for diffusion policy. Both cases, what are we after? What we are after is that we need a way to we need a generative model because we want a multimodal policy. Multimodal, not in the sense of multisensory, but modes as in statistics. If you have to go, there's an obstacle in the middle, you can go on the left, you can go on the right, but if you go on the average, you're in trouble, right? So diffusion policies are people are converging to that as the standard for doing this. And I talked about that in a previous lecture, so I won't go into more details here. Okay. This is from their this RSS 2023 paper, and this is about saying that humans are able to do this task under teleoperation. So precise tasks like pick credit card, open Ziploc, thread zip tie, turn pages of a book. So they're doing this all with a parallel geographer. And in my view, that is heroic. And it's great that you can do it, but it's a little bit like showing that a dog can ride a bicycle. It's great, but my reaction to this is what I said in my talk at Coral, which is that God did not invent us with parallel geographers. Okay, we have multi-fingered hands, and we should use them, and sooner or later robotics should do the same. So parallel geographers, the fact that you can do it with parallel geographers is very heroic, and I pat you on the back for it. But I do not see this as the right solution 5 years from now or 10 years from now. Okay, it may be the right solution now because this technology of parallel geographers is much better developed. In fact, why go for parallel geographers? Let's go for suction grippers, which are even simpler and work quite well for picking up objects. But my personal opinion is the future of research is with multi-fingered hand with tactile sensing. Okay, but I mean, to grant them the perspective from this line of work is, hey, we can do all these things with parallel geographers, and they should. Okay, the question is whether it will, what level of accuracy will this attain? So, okay, now I turn to the more recent work. So this was presented at Coral. So this is from the Google group. It's called Aloha Unleashed. And I think the other effort you should consider is the one from physical intelligence, the PI work. And both of these, they have great websites and great demos. So I will give you a flavor of this, but you should check it out on your own. So so let's talk about the Google work. So the first thing they did was that initially all the trajectories were being collected by research scientists or student interns or whatever, and that's at some point not a scalable solution. So now they hired people who came and did the trajectory collection. So I mean, this is how it goes. I mean, this is how it went in computer vision too. Like the first round of annotations, like in a data set like Pascal, was done by grad students and postdocs sitting in an office. Okay, in our Berkeley version, which was BSTS, which was even earlier, we had undergrads coming over the summer to do it. But eventually, what you need to do is you need to pay people and outsource the job, and that's how it went for computer vision. I would imagine this is the future for robotics if this is the way to success. Okay, let's see what their tasks are. I think I'm going to try to play the video in a second, but they picked fairly complicated tasks. So one is robot finger replacement. Second is hanging a shirt on a hanger. Third is inserting gears. So these are actually 3 gears that have to be inserted. Tying a shoelace. And then kitchen stacking. Well, this is a kind of fake kitchen, but they have to put some bowls together and put some the knife and fork into the cup and things like that. Okay. Big picture, there's going to be you're going to have lots of demonstrations collected from workers, and then you'll take those trajectories, put them into a diffusion framework, and train it. Okay, here is more details on the task. Shirt hanging. And then they call it shirt, 2 versions, shirt easy, shirt messy, where basically is the shirt pressed, put in a clean framework first or in a messy framework. Shoelace tying. Again, they have shoelace, lace easy, lace messy, robot finger replacement, gear insertion, random kitchen stack. I think we'll watch a movie later, so we'll see that. Shirt episode. So this is what's going on. So again, the video is more compelling. So you start from an initial state, you you kind of push the shirt into a standard configuration. You pick up a hanger, you insert, one collar into the hanger, then you do the other collar, and then you hang on a rack. Okay, similarly for other tasks. Okay, what's the architecture? Architecture is pretty straightforward, right? Nothing, no big deal. Okay, use transformers. Everybody uses transformers now. The input, there are input images. The input images are from all these different cameras. So how many cameras do we have? We have like one wrist camera on each arm. There's a top camera and there's a front camera. So those are the images. And then you run them through a simple neural net. So this is like probably some ResNet 50 or something, right? Something like that, right? Yeah. Okay, there's a proprioceptive information, which is all the joint angles, and that you run through an MLP to get an embedding. So all of this is the input for this transformer encoder. By the way, please correct me if I give some details which are wrong, because I'm going by memory and you may have read this paper more in detail. Okay, then you have this transformer decoder, and what is this doing? If you see, our goal is really to predict the actions. But the way these models work, these diffusion models work, is that you try to predict the noise. I mean, you try, and then of course by subtraction you get the action. Okay, so that's what you are seeing here. So if you see this A0 plus epsilon 0, A1 plus epsilon 1. So once I've predicted epsilon 0, epsilon 1, and so on, by subtraction I get the actions. And then they do it in chunks of like 50 times steps, and then they just do that, and then they just it's a little bit like the MPC style, right? You act, and then you are getting observations, you act again, and so on. I mean, so here one of the impressive parts are how did they manage to make it so fast? So this is some, excellent sort of software engineering and so forth to make the thing run really fast. And the fast we care about, because this is a robotic task. If you are very slow, it won't work. Right. Keep asking questions or making comments as we go. Here are the numbers. Okay, I think the numbers they range from, they're sort of in the 70s, I would call that. Okay, 75%, 70%. The shoelace task is 40%. Inserting the first gear, so they insert 3 gears in order. So the first gear insertion is 95% accurate. So usually in these sequential tasks, by the time you are finishing the last task, the probability of success goes down, because at every stage you make an error and it accumulates, right? Okay, so this gives you a flavor. And let me see. Okay, I think that this is their web page, and I'm going to scroll the web page because this way you get to see the demos. Okay, demo Aloha Unleashed. Okay, so this is the demo of the shoelace tying. Let's observe it. So there.
Think funny spent half a year just to look for a shoelace tying pattern that could be achieved by these parallel groups.
I see. I see. Yeah. Yeah. Okay. Okay. I mean, I can keep playing this forever, but so I mean, essentially everyone will have different opinions on this, right? So I think if you talk to Chelsea, I mean, she will say how amazing this is and how this proves that we do not need tactile sensing. Okay, to me, it's a little bit like when I go to the circus and I see some amazing feat. I'm impressed, but I do not want to go do it myself or make my children do this. Okay, I think I would rather have multiple fingers and tactile sensing. Okay, than develop the. As I said, I stand up and clap because you can do it, but it's not necessarily the case that I want to do it this way, right? But let me not editorialize too much. Okay. Okay. This is the robot finger replacement. So let's watch this. So they have to pull out one finger and replace it by the corrected finger. So they've taken out the bad finger and now they're putting in a new finger. So this is a delicate insertion task. Insertion tasks are delicate. Normally you want to have some sense of forces and so on. And they are managing to do this. And of course, these are the successful trials, but there'll be unsuccessful ones. Question, yeah?
Particular reason why we haven't seen diffusion policies combining both supervised and reinforcement learning? I've heard it claimed that there's some inherent reason the vector spaces don't combine.
No, there are works which try to combine with reinforcement learning, and we'll come to that. Yeah, I mean, there's no inherent reason why this cannot be done. Okay, I think I will talk a little bit later about. I'll talk about some other projects. I mean, this is all work in progress, so your idea is as good as anyone else's in terms of what to do in the future. I mean, this group has made a very strong commitment to supervised learning all the way. I personally don't buy that, but right now I'm presenting their point of view with commentary. Okay. And yeah, and then they also believe in parallel geographers, right? And no touch, no tactile. Okay, now we get to the okay, so you had enough of this example. Let me show you the shirt hanging demo. And after this, we'll have a discussion. I want to have a discussion in the class of what do you think it could do or couldn't do? So we should give the pluses and minuses of this approach. So I want that to be a class discussion. But for the moment, just observe the demos. I think these are loops, so I'll let me go up. Okay, so this is generalization. Instead of a blue shirt, we'll do a red shirt. I'm not making this up. I mean, this is actually listed as an example of generalization.
And similar to physical intelligence showed how they were collecting data for folding shirts. And then for generalization, they could hold tank top instead. Quite similar.
Yeah.
Does that mean the only thing that's generalizing is the encoder?
You mean the visual encoder?
Yeah, exactly.
Yeah, I think that's a point.
Yeah.
But because everything is end to end, so it's also the part which is the exact part.
Yeah.
It's not very, very.
This is probably called messy shirt or something. Okay. Unseen shirt. Okay. Gear insertion. So I kind of like this problem because I like these insertion tasks. And later on, we'll talk a little bit about the NVIDIA work on this, which I think, I mean, they've taken this assembly kind of problem quite seriously. And I like it because this one, the general classical belief in robotics is that this is where you want some kind of force sensing. And here they're doing it without force sensing with these fairly crappy grippers. So you have to give them some credit for that. But as you can see, so they'll put the first gear, then they'll try to put the second gear. And notice that it may not exactly align. So they may have to do a little bit of shaking. Okay, so how is that skill acquired? So essentially, they're relying on the human operators who are trying to do this task. They will try to do a little bit of this, and that way it will show up in the policy. So that slight jiggling idea is coming from the human operators trying to do this task, which is fine. I mean, I think that's okay, right? I mean, we have a lot of stuff in our current AI models, which is based on getting humans to teach the model. Okay, it's looping now. So I think here by the time you put the third gear, the probability of success has dropped off, but that's to be expected in any approach. Okay, now this is the kitchen task. So the kitchen task, let's see what's the kitchen task. So I mean, these are videos in the loop. So you wait a bit and you will see the starting configuration. Okay, starting position. So they put a cup in. Okay, so that's a success, right? So this is tidying a kitchen. Okay, so I think, let me see, I think this is probably the last demo, but so you've got the flavor now. You've got the flavor of the technology, so which is trained with teleop, then a diffusion policy, and you can see roughly what this approach can do. And if I go to these are the numbers. Okay. And you can look at the physical intelligence version of this, I mean, on their website. I have some slides on that, but same flavor, similar technology, same flavor. So let's now let's use the next. I think I want to use the rest of this hour basically for a discussion of what to expect with this paradigm. So, and the second lecture is going to be more where reinforcement learning is used. So in my mind, these are the two paradigms. So now we are focusing on the supervised learning part. So what are the key questions that I ask? Whenever, I mean, in fact, in robotics, when we have the interaction between robotics and machine learning, what are the questions we should ask? There are two, right? Generalization. And the second is robustness. So what do I mean by generalization? Generalization means that it should generalize across different objects of different size, shape, appearance, and so on. It should generalize across different tables and surfaces. It should generalize across different camera viewpoints and so on. So generalization in the setting of pattern recognition means like I have to recognize the dog in spite of the fact that it can be a different breed of dog, different pose of dog, different lighting, under occlusion, etc. So generalization should mean that. I mean, we should not change the meaning of the word generalization. It is still that meaning. What does robustness mean? Robustness has to do with the fact, robustness is not what we consider in pattern recognition, but it's something we consider in control. So when we are performing a task, things will go wrong. Life is like that. Something will go slightly wrong. And can you manage to recover from that? Okay, so robustness in this setting is really just control. When you have feedback control, it's all designed for things will go slightly wrong, and we need to fix that. We need to correct for that. We need to compensate for that. So we want that. So if both of these if both of these attributes are what we care about, and we have to judge any paradigm, I mean, this paradigm, reinforcement learning paradigm, whatever, on this. Second order are concerns like, is it easy to do? Is it convenient? And so on. I mean, those are also valid concerns. But these are the most important criteria for evaluating an approach. And for robustness, you could say, in a way, these are the numbers which tell you a little bit. So what would be our main question here? The main question here is scaling behavior. So their claim, this is what you get with like 8,000. So you get this success rate of 70% with 8,658 demonstrations. What happens if you have 15,000? What happens if you have 30,000? What happens when you have 100,000? So we have to ask the question about what are the scaling laws, right? And I don't think that this question is settled yet. I mean, we can have our intuitions and discuss it, but I think the underlying thesis of this line of work is that there are scaling laws here, just the way they existed for computer vision tasks or LLMs, and there will be similar scaling laws, and that in a tractable amount of time, right? Like if it requires 1 trillion demonstrations, you're not getting there, right? So the question is, will getting to 1 million demonstrations be okay? How much will it cost in time and money? Is it affordable? I mean, I think these are fair questions, which my expectation is that we will get the answer to this. I mean, now there are a number of people exploring these approaches. So in a year or 6 months or 2 years, you'll start to see the answer to these questions. My second, so that's one dimension. So I'm converting this to scaling laws. And scaling has worked in other settings with machine learning. We don't know how well it will work here. Generalization. What is generalization? So here is where I have my biggest concerns. The techniques are what it is doing a lot of the heavy lifting is that wrist camera, and the appearance is very specific. So the question is, how well will the approaches generalize across different objects? So in fact, I think in some of the paper, I think one of the papers, maybe it was from Shuren Song's group, where there is a discussion of what they call narrow generalization versus broad generalization. So narrow generalization is at that same site. So let's say at Google, they've got this platform where they're doing all this work, right? But this is something which is at Google, right? And they probably set up multiple versions of this so that different teleoperators could be used to collect trajectories. Now, my home, where I fold my laundry, doesn't look anything like this, right? And neither does your home or anyone else's home. So the generalization has to work for different object types, for different homes, for X, Y, Z, right? The question here is, will this work? Okay, and then it again gets tied back to the scaling question. Will it scale? Is scaling the answer to everything? So if scaling is the answer to everything, scaling will deal with generalization and scaling will deal with robustness. So the error rate comes down, so we're happy on the robustness. It works for many different kinds of objects. That is the generalization question. Okay, so I think I've spoken enough. Let me just show you the version from physical intelligence. So this is our first generalist policies, a very catchy name, Pi0. And what do they show? So they show things like this. Okay, so they pull some clothes out of a washing machine. They are folding. Let's see. Is there more demos here? I mean, there's some other stuff about using different robot embodiments, but to me, that's not the central issue. The central issue is, you know, I mean, if you can't do the task well with one robot, then you're not going to do it better with 8 robots, right? So this is one of their examples, folding a cardboard box. Okay, let's see. Okay, yeah, let's go for, so they have kind of these demos in the most slightly more quote open world settings. But let's do a discussion here. I'd like people to express their points of view, or whichever you can, you know, what you like, what you don't like, what your betting is. We should take down everyone's predictions and we can check back in 2 years from now, you know. Okay, anyone wants to speak up? And just speak loudly, because that way we can.
I think it's definitely good that it's deployed in a home-like environment, and you know, you can take out clothes, put them in the dryer. So maybe we're getting closer to seeing robots deployed in the home. This is a task. When you tell people about robots getting more advanced, they think about stuff like this.
Yeah.
Can I have it at home, help with washing or cooking?
Mhm.
So I think it's a good start that they attempted the task.
Yeah, no, that I agree. I want to say that I mean, in most of the classical robotics work is for the factory floor or the warehouse floor, and here we are going for the home, and which I believe is interesting and important, right? And we are all after this goal of the home robot. So that I agree with. I want to state one more thing which I like, which is that it's just that the range of tasks that are studied is being expanded. That's a good thing. Okay. In fact, in one of my earlier lectures, I had this set of common atomic skills, mainly because I'm trying to push that robotics is more than pick and place. So I think them trying out all these tasks is great. I think what the one interesting thing which comes from that is just specifying the task is hard. So for me as a human to tell the computer to do this task, how do I do that? That is a challenge. It's really a challenge, particularly for reinforcement learning approaches, because it has to be done by reward shaping. Whereas demonstrating a task, either with a human just doing it and a camera observing, or through this teleop, these are very natural ways to specify a task. So this is an aspect of the solution. It's not unique to them, but I like this. I think my concerns are to do with these 2 questions: generalization, robustness, and what will be the scaling behavior. But I want to hear other people's opinions, not mine. Yeah.
I feel like in robotics right